Welcome. In this session, we'll dive into problem number 93, restore IP addresses. This is a fascinating problem that challenges us to generate valid IP addresses from a given string of digits. We'll explore different approaches to solve it, understand the trade-offs, and identify the optimal solution. Let's get started. In this problem, you are given a string S that consists only of digits, and your goal is to generate all possible valid IP addresses by inserting dots into the string. A valid IP address has exactly 4 segments, separated by dots. Each segment must be an integer between 0 and 255, inclusive, and it cannot have leading zeros. For example, the string 2552551135 can be converted into valid IP addresses like 255.255.11.135 and 255.255.111.35. The task is to identify all such possibilities and return them as a list of strings. The input string S will have a length between 1 and 20, and the output should be a list of valid IP addresses that satisfy these conditions. To understand this better, let's look at some examples. For the input S equals 255.255.11135, we can form 2 valid IP addresses, 255.255.11.135 and 255.255.111.35. Each segment of these IP addresses falls within the range of 0 to 255, and none of the segments have leading zeros. Now, consider the input S equals 0000. Here, the only valid IP address is 0.0.0.0, where all segments are single-digit numbers, and again, there are no leading zeros. These examples highlight how the string can be divided into 4 valid segments that meet the problem's requirements. Another example is S equals 101023. Here, we can form 5 valid IP addresses, 1.0.10.23, 1.0.102.3, 10.1.0.23, 10.10.2.3, and 101.0.2.3. Each of these addresses is valid because all segments are within the range of 0 to 255 and do not contain leading zeros. The constraints of the problem are also important to keep in mind. The string S must have a length between 1 and 20, and it can only contain numeric digits. Each segment must fall within the range 0, 255, and leading zeros are not permitted, except for the single-digit 0. Additionally, the string must be split into exactly 4 segments, no more and no fewer. Now, let's discuss some edge cases. If the input string S has fewer than 4 characters, it's impossible to form a valid IP address because you can't create 4 segments. For example, with S equals 123, the output will be an empty list. Similarly, if the string is too long, such as S equals 1234567890123, it's also impossible to form a valid IP address since there are not enough digits to divide into 4 segments while keeping each segment within the range 0, 255. Another important edge case involves leading zeros. For example, in S equals 010010, valid outputs are 0.10.0.10 and 0.100.1.0, where no segment contains leading zeros. Finally, if the input string consists entirely of zeros, like S equals 0000, the only valid IP address is 0.0.0.0. These scenarios highlight the importance of handling special cases while solving this problem. To tackle the problem of restoring IP addresses, we first consider the brute force approach. The intuition here is simple: generate all possible ways to insert 3 dots into the string, dividing it into 4 segments. Then, for each combination, check if all the segments are valid IP components. A valid segment must be an integer between 0 and 255, and it can't have leading zeros unless the segment is exactly 0. While this approach is straightforward, it quickly becomes inefficient. The number of ways to place the dots grows as the cube of the string's length, resulting in O, n cubed, combinations. Since most of these combinations produce invalid IP addresses, a significant amount of computation ends up being wasted. Now, let's look at a more refined solution, the backtracking approach. Here, we construct valid IP addresses incrementally. Starting from the first character, we try placing a dot after 1, 2, or 3 characters, ensuring that the resulting segment is valid. This process is repeated recursively until we form 4 valid segments and process the entire string. valid combinations are then added to the result. There are a few key observations that guide this approach. Each segment must meet the same criteria as in the brute force method, being between 0 and 255 without leading zeros. Additionally, since an IP address has a maximum of 12 characters, strings longer than this can be immediately discarded. The advantage of backtracking lies in its ability to prune invalid paths early, saving time and computational resources. Its time complexity in the worst case is 3 to the power of 4, as we explore up to 3 splits per segment for exactly 4 segments, and the space complexity is 4, accounting for the recursion stack. An alternative method to solve this problem is iterative generation. This involves using nested loops to generate all possible 4-segment combinations. For each combination, we check its validity before adding it to the result. While this avoids recursion, it introduces deeply nested loops, making the implementation less intuitive and harder to scale for larger problems. Given the options, we chose the backtracking approach as our strategy. This method is both efficient and clear, avoiding the combinatorial explosion of brute force by pruning invalid paths early. Compared to iterative generation, backtracking is more structured and easier to implement without relying on unwieldy loops. When comparing trade-offs, brute force is conceptually simple but suffers from inefficiency due to wasted computation on invalid cases. Backtracking, on the other hand, strikes a balance between efficiency and simplicity by focusing only on valid paths, making it both scalable and intuitive. While iterative generation avoids recursion, its lack of clarity and scalability makes it less appealing. Ultimately, backtracking emerges as the most efficient and scalable strategy for solving this problem, making it the optimal choice. To solve the restore IP addresses problem, we need to take a string of digits and insert exactly 3 dots to create 4 segments, each of which must represent a valid IP address component. A valid component is an integer between 0 and 255, with no leading zeros unless the segment is exactly 0. To check for validity, we define a helper function called is_valid. This function ensures that the segment does not start with 0 unless it's the single digit 0, and that the integer value of the segment falls within the required range. With this helper function in place, the next step is to generate all possible ways to place 3 dots in the string. This involves iterating through all possible positions for the first, second, and third dots, an approach we'll explore further in the algorithm design. Once we identify positions for the 3 dots, we split the string into 4 parts. For example, if the dots are placed at indices I, j, and k, the 4 parts would be part 1, part 2, part 3, and part 4. It's important to ensure these indices are valid and that the string is divided into precisely 4 segments. After splitting, we validate each of the 4 parts using the is_valid function. If all parts qualify as valid IP address segments, we combine them into a complete IP address, formatted as part 1. Part 2. Part 3. Part 4, and add it to the result list. Finally, after iterating through all possible dot placements, the algorithm returns the list of valid IP addresses. This process ensures that every possible combination is tested, while filtering out invalid results using our validation logic. The algorithm incorporates several optimizations to improve efficiency. First, we limit the ranges for I, j, and k based on the constraints of an IP address. Each segment can have at most 3 digits, so we avoid unnecessary iterations by enforcing these bounds. Additionally, we use early termination to handle edge cases if the string is too short to form 4 segments or too long to fit within the 12-character limit of an IP address. We immediately return an empty list. The is_valid function also ensures that segments with leading zeros, such as 01 foot or 001, are excluded. By structuring the algorithm in this way, we eliminate redundant checks and focus only on viable candidates. The result list is used to store valid IP addresses, and temporary variables manage the current segments during processing. As for complexity, the algorithm is bounded by n cubed, due to the iteration over all possible combinations of 3 dots, while the space complexity is determined by the number of valid results generated. The space complexity of this algorithm is minimal, with 1 for temporary variables and m for the result list, where m is the total number of valid IP addresses found. When handling edge cases, we immediately return an empty list for strings with fewer than 4 or more than 12 characters, as they cannot form valid IP addresses. The validation logic ensures that segments with leading zeros, such as 01 foot, are rejected, and since the input is assumed to be numeric, there's no need to check for non-numeric characters. For example, given the input string 25525511135, the algorithm systematically tries all valid ways to place 3 dots. After filtering out invalid combinations, it identifies the valid IP addresses 255.255.11.135 and 255.255.111.35. These are returned as the final result, demonstrating the effectiveness of the algorithm in generating all possible valid IP addresses from the input string. The provided code is a solution to LeetCode problem number 93, Restore IP Addresses, which generates all possible valid IP addresses from a given string S by placing exactly 3 dots. The solution uses a backtracking approach to explore all possible combinations of valid IP segments. The Restore IP Addresses function defines 2 helper functions, is_valid and backtrack. The is_valid function checks if a given string segment is a valid IP address segment. It ensures the segment is between 0 and 255 and does not have leading zeros unless it is 0. The backtrack function is the core of the backtracking algorithm. It takes the current start index in the string and the current path of segments being built. If the path contains exactly 4 segments and all characters of the string have been used, it adds the joined segments to the result list. Otherwise, the function explores segments of lengths 1, 2, and 3 starting from the current index. For each segment, if it is valid, the function recursively calls itself with the updated start index in path. The result list stores all valid IP addresses generated during backtracking. The initial call to backtrack starts with an empty path and index 0. The function ultimately returns the result list containing all valid IP addresses. This implementation handles edge cases such as strings that are too short or too long to form an IP address, e.g., fewer than 4 or more than 12 characters. The use of recursion ensures all possible partitions are considered efficiently, while the validation function ensures only valid IP addresses are included in the result. Here, we start implementing the solution for restoring valid IP addresses by defining the Restore IP Addresses method. This method takes a string S as input and returns a list of valid IP addresses. To achieve this, we initialize an empty list called result to store the valid IPs and call a helper method named backtrack. The backtrack method handles the recursive exploration of all possible segmentations of the input string. It takes 4 parameters, the input string S, the current starting index start, a temporary list path to store the current segments being built, and the result list to collect valid IPs. Inside backtrack, we first check if we have exactly 4 segments in path. If so, and if all characters in S have been used, we join the segments with dots and add the resulting IP to result. Otherwise, we iterate through possible segment lengths from 1 to 3. For each length, we ensure that it doesn't exceed the remaining substring and extract the segment. If the segment passes validation, we add it to path and recursively call backtrack with the next starting index. This is where we begin constructing the possible valid IP addresses. If the segment passes validation and is added to the path, we proceed to explore further by calling backtrack recursively with the updated starting index. After the recursive call, we remove the last segment from path to backtrack and try other possibilities. The isValid function is responsible for verifying whether a segment is a valid part of an IP address. A segment is considered valid if it does not start with a leading 0, unless it is exactly 0, and its numeric value lies between 0 and 255. For segments with more than 1 character, any leading zeros make the segment invalid. In the isValid method, we check these conditions and return true or false accordingly. Finally, the main method demonstrates how the solution works by testing it with a sample input string. For the input 25525511135, the program prints the list of valid IP addresses, showcasing how the algorithm effectively generates all possible combinations and filters out invalid ones. This implementation uses recursion and backtracking to explore all segmentations systematically while ensuring that only valid IPs are returned. Let's continue. Let's continue. Let's continue. Let's continue. The time complexity of restoring valid IP addresses is primarily driven by the recursive backtracking process and the validation of IP segments. To begin, the recursive backtracking systematically explores all possible ways of partitioning the input string into exactly 4 valid segments. Each segment can have a length of 1, 2, or 3 characters, so for a string of length n, the recursion tree will have a branching factor of 3, representing the 3 possible segment lengths. Since we are restricted to 4 segments for an IP address, the depth of the recursion tree is 4, resulting in at most 3 raised to the power of 4, or 81, possible paths through the recursion tree. Additionally, at each recursive step, the algorithm validates whether the current segment is a valid IP component. This validation involves basic operations like integer conversion and range checking, both of which are constant time operations. With a maximum of 81 segments to validate, the total cost of these validations remains constant, making their contribution to the time complexity negligible overall. When we combine these factors, the overall time complexity is determined primarily by the recursive exploration, which is capped at 81 paths due to the constraints of IP address formatting. This constant upper bound means that for strings within the valid length range of up to 12 characters, the time complexity remains 1. Next, let's consider space complexity. The primary contributors to space usage are the recursive call stack and the storage required for the results. The recursion depth is limited to 4, corresponding to the 4 segments of an IP address, and each call uses constant space for local variables, leading to a total stack usage of 4, which simplifies to 1. For storing results, the algorithm generates at most 81 valid IP addresses for strings of maximum length. Each IP address is a string of fixed length, requiring constant space for storage. Thus, even in the worst case, the space required for storing results is also constant. Combining these, the overall space complexity is 1. This brings us to a comparison with a brute force approach. A naive solution would generate all possible substrings of the input string and then filter out invalid combinations. For a string of length n, this approach would need to evaluate n to the power of 4 combinations to account for every possible way of dividing the string into 4 parts, and each combination would require n time for validation. This results in an overall time complexity of n to the power of 5, which is highly inefficient. By contrast, the backtracking approach is far more efficient. By limiting the recursion depth to 4 and immediately validating segments as they are generated, the backtracking method avoids exploring invalid paths unnecessarily. This enables it to achieve constant time complexity for strings within the valid length range, making it a significant improvement over the brute force method. To conclude, let's analyze the best, average, and worst-case scenarios for this algorithm. In the best case, where no valid IP addresses can be formed, such as when the input string is excessively short or contains all zeros, the recursion terminates quickly, resulting in minimal computation and a time complexity of 1. In the average case, typical input strings lead the recursion to explore a subset of the 81 possible paths, keeping the complexity at 1. Even in the worst-case scenario, such as a string like 111111111111, where all paths need to be explored, the constant upper bound of 81 paths ensures 1 complexity. Mathematically, this holds because the recursion tree is limited to 81 paths, each requiring constant time for validation and storage. For strings longer than 12 characters, the algorithm terminates immediately, as such strings cannot represent valid IP addresses, further reducing computation. Therefore, the time and space complexity remain constant across all cases for valid input lengths. When working on restoring IP addresses, there are several common mistakes to watch out for. First, not validating each segment properly is a frequent error. For example, a segment like 1 foot is invalid due to the leading 0, but some implementations might overlook this. Another issue is overlooking input edge cases. Strings that are too short, like having fewer than 4 characters, or too long, with more than 12 characters, cannot form valid IP addresses. It's important to handle these cases efficiently to avoid unnecessary computations. Additionally, incorrectly handling empty segments is another common pitfall. For instance, splitting a string like 255 might result in invalid segments if empty parts are not accounted for. Finally, confusing index bounds can also be problematic. Errors often happen when calculating the range of indices for valid splits, leading to out-of-bounds errors or even duplicate calculations. Staying mindful of these details can save a lot of debugging time.
Another challenge is inefficient backtracking.
Some solutions explore paths that could have been pruned earlier, wasting precious computation.
For example, if the first segment exceeds 255, there's no point in exploring further splits down that path.
Now, in interviews, it's crucial to recognize key patterns, such as the requirement for exactly 4 segments, each between 0 and 255, with no leading zeros except for the single-digit 0. Optimizing backtracking by pruning invalid branches early is a great way to make your solution more efficient and demonstrate thoughtfulness.
Be ready to discuss edge cases, like strings that are too short, too long, or contain invalid splits, as these are often focal points in interviews. If there's time, you can also discuss trade-offs between approaches, such as brute force versus backtracking, or even iterative generation, to show your understanding of both efficiency and readability. This problem shares similarities with other LeetCode challenges that involve generating valid combinations or partitions. Examples include generate parentheses, palindrome partitioning, letter combinations of a phone number, and subsets. If you're comfortable with these, you'll notice overlapping techniques that can be helpful here. Now, in terms of approaches, brute force involves generating all possible placements of 3 dots, which results in n³ splits to check. While straightforward, it's inefficient, especially for longer strings. A more advanced method is backtracking, where you recursively build segments and validate them as you go. By pruning invalid paths early, this approach avoids unnecessary calculations and is highly efficient. Alternatively, iterative generation uses nested loops to create segments.
Though less elegant than backtracking, it can be simpler to implement and debug, making it a viable option in certain scenarios. When comparing the trade-offs between approaches, brute force is often the easiest to implement but falls short in efficiency, especially for larger inputs. Backtracking, while more optimal, requires careful handling of recursion to avoid errors. On the other hand, iterative solutions can be easier to debug since they lack recursion's complexity, but they may not be as modular or clean as recursive approaches.
For problems like restoring IP addresses, recursion tends to result in more concise and maintainable code, particularly when dealing with partitions or combinations.
Ultimately, the best approach depends on the specific constraints of the problem and your comfort level with these techniques.
Great work!
To wrap up, we summarized our approach to solving restore IP addresses, highlighting key insights and lessons learned.
Remember to practice similar problems to master backtracking techniques. Thank you for your time, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!